Hello guys, a big thank you for supporting my channel. You have made me very popular and am grateful. Thanks to the students all over the world, especially Pakistan, India, Bangladesh, Rwanda, Zambia to mention but a few. You have been the greatest fans in my teaching career. Thank you for always watching my videos, giving suggestions on, asking questions, making constructive criticism and corrections. I love you so much and wish you success in your academics. Continue sharing the channel with anyone involved with Cambridge Physics. If you are new to my channel, please consider to subscribe and share and like the videos. Hit that like button and bell icon to keep updated. Thank you so much.
Hello guys, my name is IBM and I think this is going to be lesson number 3, and I think this is going to be the last lesson. I expected lesson number 2 to be the last, but then I got really very tired, so I decided to create lesson 3 as the last lesson of simple harmonic motion. But this is going to be very short because it's going to concentrate on simply one part of simple harmonic motion, which is entirely energy changes during simple harmonic motion. So we want to explore and understand the energy of a body which is describing simple harmonic motion. Energy of a body performing simple harmonic motion is what we want to really explore in more details. So let's start. So let's consider we are going to consider a simple pendulum as one of the easiest way of understanding the energy changes during simple harmonic motion. Of course, when a body is stretched, or if a body undergoes simple harmonic motion, um, the body keeps changing positions. That means the displacement keeps changing as the acceleration changes and as the velocity changes. That means the energy forms involved keep on changing. So during simple harmonic motion, there is a constant interchange of energy between two forms that could be gravitational potential and kinetic energy, as we are seeing this animation here. So if we consider this as the reference point, I'm going to consider this point here as the reference point, where we assume that if this is the reference point, the mass raises up to a certain point. In other words, the gravitational potential energy increases in one direction, and we can also think of it as increasing the other direction, maybe. But if we take this as the reference point, then we would say this would be the potential energy here would be considered to be zero if it is a reference point. And at the reference point here, the kinetic energy also becomes zero because it momentarily goes to zero, or it momentarily comes to rest. However, if we consider this as the reference point where x is going to be equal to zero, then here we assume that the displacement would be zero, so the potential energy would be considered to be zero, and the body passes equilibrium position with maximum speed, so the kinetic energy will be zero when x is equal to zero. Then when it raises to the highest point, it means potential energy becomes maximum because the vertical height becomes maximum, and then we would say that kinetic energy is going to be equal to zero because the body momentarily stops. This is kind of confusing, not until we use a simple pendulum to demonstrate this. So The elastic potential energy keeps on changing as the body raises to a certain point and then it falls to a certain point, because the elastic potential energy, as you saw in a unit called deformation of solids, the elastic potential energy depends on the spring constant. In that case, if you consider a spring constant. But to fully understand the energy changes which are involved during simple harmonic motion, let's just consider a simple pendulum like this one. So if we take this as our reference point here, where the body is in equilibrium, here the displacement x is equal to 0. And if the displacement x is equal to 0, the vertical height h is going to be 0 because this is a reference point. So at this point, the kinetic energy is going to be maximum, reason because the body passes equilibrium position with the maximum speed. But potential energy is mgh. So at this point, potential energy is going to be actually 0 because h is 0. So if we release the object, say from the highest point in position A, it is at the highest point, the highest value of h from the equilibrium position or from the reference point. So the potential energy here is maximum, and is going to be mg times h, and the kinetic energy is going to be 0, because at the highest point the velocity becomes 0, so the body momentarily stops before it changes direction to move in the opposite direction. So at the highest point, we have entire potential energy as kinetic energy is 0. Then as the body moves downwards, it gains speed. So at equilibrium position where x becomes 0, the body passes equilibrium position with the maximum speed. So kinetic energy becomes maximum. Then the body moves to the other side. That means it moves to the other extreme end, where again it gains maximum potential energy because it reached the highest point from the reference level. So potential energy gain goes to maximum and kinetic energy goes to 0. So energy is just leaving one form to another form. So we are referring to energy changes here as potential energy decreases, kinetic energy increases, but the total sum is going to be the same because the law of conservation of energy is not going to be violated at any particular point. So as potential energy decreases, kinetic energy is going to increase. As kinetic energy decreases, potential energy is going to increase, but total energy is going to be constant. For a spring that we are considering here, there are three forms of energy we are considering here. There is elastic potential energy, there is gravitational potential energy, and there is kinetic energy. So if we consider EP as the elastic potential energy or the gravitational potential energy, then in that case we should be very, very, very careful. When the spring is stretched, the elastic potential energy becomes maximum when x is equal to x naught. And also it also becomes maximum when x is equal to positive x naught. But the elastic potential energy can be considered to be 0 if the body is at equilibrium position. But how about the gravitational potential energy? So that is a point of contention and something that we need to pay attention to. The gravitational potential energy depends on the vertical height. So it will depend on what are we considering to be our reference point. If we consider the lowest point as a reference point, then the gravitational potential energy here will be considered to be 0. And of course, at the lowest point, the mass is momentarily going to be at rest. So still, both kinetic energy and potential energy will be 0. But at the highest point, the mass momentarily stops. It's only the kinetic energy which will be 0. But the gravitational potential energy will be maximum because it depends on the vertical height from the reference point. If we consider the equilibrium position here, the body passes equilibrium with maximum speed, so the kinetic energy will be maximum. But if we consider elastic potential energy at the reference point, then the elastic potential energy would be 0. However, if we consider the lowest point as the reference point, at this point at the center, elastic potential energy would be 0, but our gravitational potential would be half of maximum. So to understand this, maybe let's use a simpler animation. These animations show the energy changes which occur during oscillation of this mass on a spring, for example. Uh, as the spring stretches further and further, I want to come up with an equilibrium position. Now the spring is oscillating between two fixed points, so I want to come up with an equilibrium position. Okay, so at the extreme end of the oscillations, I want you to just mark the extreme points of the oscillation. The extreme points of the oscillation, what happens to the kinetic energy in all cases? At the extreme points, here velocity becomes zero. At the extreme points, velocity also becomes zero. So we're always going to notice that at extreme points, the kinetic energy will always go to zero. But then, if we use this as the reference point, when the body comes to the extreme point at the bottom, potential energy, when you look at the gravitational potential energy, is always going to zero. And when it rises to the highest point, the gravitational potential energy is always going to maximum. But how about the elastic potential energy? The elastic potential energy is going to elastic potential energy is depending on how much this spring is being stretched. So notice that if the stretching is maximum, the elastic potential energy also goes to maximum. When there is no stretching, the elastic potential energy goes to zero. So energy is just changing from one form to another, but we notice that total change or the sum of all the energy changes is not changing. It is going to remain constant. So it means energy is changing from one form to another, but the total energy is going to remain constant. So let's begin by understanding how we obtain kinetic energy. Kinetic energy of a body performing simple harmonic motion. So let's begin with the kinetic energy of a body performing simple harmonic motion. How do we arrive at the kinetic energy of a body performing simple harmonic motion? Okay, so for a body performing simple harmonic motion, one of the things we need to note is that we know that from the expression which is given in the list of formula, the speed, or we know that kinetic energy is equal to a half m v squared in general. But from the expression that is given, we know that v is equal to omega square root of course, this is plus or minus, square root of x naught squared minus x squared for velocity. So when I square the velocity, it means v squared is going to be omega squared into x naught squared minus x squared. So we know that the kinetic energy for the body performing simple harmonic motion is going to be a half times m, where there is v squared, I'll put omega squared into x naught squared minus x squared. So this equation is not given in the list of formula, but since I know that kinetic energy is a half mv squared, and the equation for velocity of a simple harmonic motion is given as v equals plus or minus omega root of x naught squared minus x squared, I should be able to combine the two and I obtain an expression for kinetic energy. So since I know the expression for kinetic energy, since we now know the expression for the kinetic energy as equal to a half m omega squared into x naught squared, therefore we should be able to sketch a graph of kinetic energy against maybe displacement. We should be able to come up with a graph of kinetic energy against displacement from that equation. So of course, when x equals to 0, what is the kinetic energy? So when I put here 0, it means kinetic energy is going to be a half m omega squared x naught squared, and you see that all these ones are constants. We shall later on call this one the maximum energy or total energy, which is going to be E naught. So when kinetic energy is when x is equal to 0, that is the body is passing equilibrium. So when x is equal to 0, the kinetic energy is equal to maximum energy or maximum total energy, which is going to be simply E naught. Then when x equals to plus or minus x naught, what is the kinetic energy? So when I put where there is x, I put there x naught, this becomes 0. So this will become 0. So you have 3 points to consider. Number one, you have 0 and E naught, and you have plus x naught and 0, and you have minus x naught and 0. So these are the points we need to sketch. Remember, displacement is a vector quantity, but energy is a scalar quantity. So we shall not have the negative part of energy, but we shall have the positive and negative part of displacement. So if I try to sketch this graph, I come up with something similar to this. So this is going to be E naught. That is when x is equal to 0. The kinetic energy, yes, the kinetic energy is going to be the maximum energy, which is E naught. So this is the graph of kinetic energy against displacement. Is a dome-shaped curve, just like that one there. So you don't need to cram the graph, you just need to sketch it from first principles from the equation. Because if you sketch a graph of kinetic energy against displacement bearing in mind that kinetic energy is a scalar quantity, so I don't need a negative part, but displacement is a vector quantity, and displacement varies between negative maximum and positive maximum through 0. So just check when x is 0, what is kinetic energy? It is maximum. Then when x is positive or negative x naught, when I substitute in the equation, kinetic energy goes to 0. That's why the graph touches this point here and this point. And the only way we can join this is by drawing a smooth curve, just like that one. So that will be the graph for kinetic energy against displacement. Let us also see what happens to the potential energy. So for potential energy, to derive a simpler expression for potential energy, we shall consider one, I'll simply consider the equation for simple harmonic motion, where we know that acceleration is equal to negative omega squared times x. And number two, by Newton's second law, force is equal to mass times acceleration. And when you combine, you have that the force is equal to mass negative m omega squared times the acceleration as the equation for the force. Sorry, I have substituted for a, so it is negative m omega squared times x. Okay, but if we consider the work done against the restoring force to move the mass m by a distance x, the work done, of course, we know that work done by the force F to move a mass through a distance x, work done is given by force times distance. But since here the force, because further extension, you must go on increasing the force, then we shall take the average of this. So this is going to be F over 2. Then we multiply this by x. So the work done is going to be the average force, then times the distance. So the work done against the restoring force is going to be the average force times the distance. So the work done is F over 2 times x. But ignoring the minus, F is going to be m omega squared times x. So that means the work done therefore becomes m omega squared x, that is the force, divide this by 2, then times another x. So the work done is going to be equal to a half m omega squared times x squared. So this work done is going to be stored, or is what is going to be stored as the potential energy, or the potential energy of a body performing simple harmonic motion. So the potential energy is going to be a half m omega squared x squared. So it's like the potential energy is directly proportional to the square. The potential energy is going to be directly proportional to the square of the displacement. So this means this is going to be it's not also going to be a straight line. So we can check this. What happens to the potential energy when x equals to 0? Of course, this is going to be equal to 0. Potential energy is 0 when x equals to, because they are directly proportional. When x equals to positive or negative x naught, it also means potential energy is simply going to be a half m omega squared x naught squared, and it is all going to be positive. So this is going to be E naught. This is going to be the maximum. So when we sketch the graph, of course, remember this is a scalar quantity. Therefore, since it's a scalar quantity, we don't need the negative part of energy, but displacement is a vector quantity, so we need both positive and negative. So when we sketch the graph, we shall come up with a graph which looks like this. When x equals to 0, potential energy is going to be 0, because potential energy is a half m omega squared x squared. And when x is negative x naught, potential energy is maximum. So here, where this curve is stopping, this corresponds to E naught, which is the maximum potential, maximum energy. So it's like the maximum kinetic energy is the same as the maximum potential energy, which will be a half m omega squared times x naught squared. This is maximum energy. The maximum potential energy is the same as the maximum kinetic energy, which is going to be half m omega squared x naught squared, which is a constant because the mass of a body is a constant, angular velocity is a constant, maximum displacement is a constant. So it's like total energy is always going to be a constant. And whenever potential energy is maximum, kinetic energy is going to be zero. And whenever kinetic energy is zero, whenever kinetic energy is maximum, potential energy is going to be zero. So to fully understand this, then let's put them on the same scales. Let's put the two graphs on the same scale. So let's have both potential energy and kinetic energy on the same axis. So a graph of potential energy and kinetic energy on the same axis. So for potential, remember for potential energy, when x is zero, potential energy is zero because potential energy, we know that potential energy is equal to a half m omega squared x squared. And we have seen that kinetic energy is equal to a half m omega squared into x naught squared minus x squared. So when x is zero, potential energy is zero. But when x is zero, kinetic energy is maximum. So this was the maximum energy. So the graphs look like that. And of course, when we sum up the two to find the total energy is the sum of kinetic energy plus potential. So when we add the two equations, we come up with that expression here, which we have already derived before. When I sum up all this, I come up with that expression for total energy. And I want you to notice that everything there is a constant. So it is not by coincidence that total energy remains constant. Therefore, we can scientifically say that the law of conservation of energy has not been violated because the total energy is remaining constant because a half m omega squared and x naught squared are all constants. So all m omega squared or omega x naught and of course a half are all constants. These are all constants, which means total energy is a constant. Because all of those quantities are constants, so total energy is going to remain a constant. Therefore, it's not by coincidence that is a constant. The law of conservation of energy has not been violated. So I want you to notice just that the kinetic energy is maximum when displacement is zero, and potential energy is maximum when displacement is maximum because potential energy is the actual proportion to the displacement squared. And also notice that at any point on this graph, total energy will be potential plus kinetic. It will always be the same value at any point. The total energy at any point on this graph, total energy will always be the same. It will always be constant. You notice that whenever kinetic goes to zero, potential is maximum. So the sum is the same. When kinetic goes to zero, potential goes to maximum. When potential goes to zero, kinetic goes to maximum, and the total is always going to remain the same. So we say total energy is going to remain a constant throughout, which means the law of conservation of energy has not been violated. The law of conservation of energy has not been violated. Let's try to put this let's try to investigate the variation of energy with time, maybe for a few oscillations or one complete oscillation. We have seen variation of energy with displacement. How about variation of energy with time? So let's look at variation of energy with time. How does energy vary with time? Let's consider a simple pendulum for simplicity. And we want to explore. We are going to divide this into we're going to divide this into several cycles. And let's say t equals to 0. We can say t equals to 0 when the body is just passing equilibrium. So t equals to 0 when the body is passing here. That is t equals to 0. Let's say the body is considered when it is moving to the right hand side. Let that be positive. So this is going to be positive x naught, that is at maximum displacement. This is going to be at t equals to a quarter of a cycle. Then when it comes back to equilibrium, this is going to be at t equals to a half of a cycle. Then it continues to the other end, which is going to be at t equals to 3/4 of a cycle. And then it comes back, that is after t equals to a period. It reaches back at t equals to a period. That is a complete cycle. Before we even sketch, you can evaluate this and see. At t equals to 0, the body is passing equilibrium, which means kinetic energy is maximum. This is maximum. Potential energy is going to be 0 because potential energy depends on the maximum displacement, the vertical height from equilibrium position. Then when we look at t equals to a quarter of a period, at the maximum point, at the highest point, velocity goes to 0. That means kinetic energy is going to be equal to 0. At the highest point, the vertical height is greatest, so it means potential energy is going to be maximum and to be E naught. Let's talk about t equals to that this was a quarter cycle. Let's say a half a cycle. At a half a cycle, again, the body is passing equilibrium where the speed is maximum, so kinetic energy again becomes maximum, E naught. And whenever kinetic energy becomes maximum, the potential energy becomes 0. Let's check t equals to 3/4 of a cycle at the highest point on this position here. So kinetic energy again goes to 0 because at the highest point velocity goes to 0. But at the highest point, the height above the reference point is maximum, so the potential energy is going to be maximum. Then at t equals to 1 cycle now, that is after 1 period, of course, again, the body is passing equilibrium with maximum speed, so kinetic energy becomes maximum. And again, potential energy goes back to 0. And the process continues until maybe the oscillations stop, if they really stop. However, in all cases, in the first case, total energy is going to be E naught plus 0. Second case, total energy is E naught plus 0. In all cases, total energy is simply the sum of kinetic plus potential. So it is still going to be a horizontal line. So if I was to sketch a graph of kinetic energy against time, or energy against time for potential, kinetic, and total. So for kinetic energy, when t equals to 0, okay, so I reversed this. For this graph, it means timing starts from here, but it's almost the same thing. So the one I have just discussed there, it would look like something like this. Let me try to sketch it here. So here, this one is when here t equals to 0, the body is passing equilibrium. Is at maximum displacement. The one I've just discussed would look like this. At t equals to 0, the body is passing equilibrium, so it is just the opposite. So this would be kinetic energy. I'll divide this into 4 parts. This is 0, a quarter, a cycle. This will be half a cycle. This will be 3/4 of a cycle, and this is going to be 1 cycle. So I'm starting at t equals to 0, the body is passing equilibrium where velocity is maximum. So kinetic energy is going to be maximum. So the graph starts from there. Then at a quarter cycle, the kinetic energy goes to 0. Half a cycle, it becomes maximum on the other side. Sorry, it is a scalar quantity, so the negative part is not necessary. I don't need the negative part. This is not necessary because this is a scalar quantity, energy is a scalar quantity, so I have to just sketch the upper part of this graph. And both of them are scalars, so I have energy against time. Both of them are scalars. So I have 0, a quarter of a cycle, half of a cycle, 3/4 of a cycle, and then 1 cycle. Okay, so at t equals to 0, I've considered the body passing equilibrium, and I'm saying kinetic energy is maximum when the body is passing equilibrium, but potential energy is 0 when the body is passing equilibrium. Then at 3/4, the body goes to the highest point, kinetic energy goes to 0. Half a cycle, it comes back to equilibrium, kinetic energy goes back to maximum. 3/4, it goes to the highest point, kinetic energy goes to 0. Half a full cycle, it comes back to equilibrium, kinetic energy goes to maximum. So the graph would look like this. This is just a sketch. So it continues like that. Then for potential energy, I will change the color for potential energy. If we start at t equals to 0 from equilibrium, potential energy is 0. So this would be this point. A quarter cycle is at the highest point, so it will be here. Half a cycle, it comes back to equilibrium, potential energy goes to 0. 3/4 is at the highest point, so it goes to maximum displacement. It goes to maximum. A full cycle, the body is passing equilibrium, so potential energy goes to 0. So this would be something like this. And so on and so forth. So you notice that this graph here is the same as this, only that here timing, t is 0 when the body is at maximum displacement. Yet here t is 0 when the body is at equilibrium. When the body is at equilibrium. So green was kinetic energy and blue was potential energy. But of course, total energy is the sum of the two, so total energy is going to always be a horizontal line because energy is going to remain constant. So the total energy will be just a horizontal line. So that will be the total energy. This will be the total energy, which I wrote as E naught. Okay, so I am saying you should be able to sketch such a graph. You should be able to sketch such a simple graph. Okay, so that is a graph of energy against time. So you should be able to sketch a graph of energy against time for both kinetic, potential, and total on the same axis for one period. When we say one period of a cycle, that is one complete cycle. So this is 0, this is a quarter of a cycle, this is half of a cycle, this is 3/4 of a period of a cycle, and then one complete period. So this simple pendulum makes sketching of this graph very, very easy, as shown there. Then this is a summary of the variation. So let's summarize the variation with the displacement and time, including energy. So let B be the equilibrium position or the reference point or the fixed point. And we can say movement to the right is positive and movement to the left is going to be negative. So at B, time is equal to 0 when we are at B. The displacement is 0 when we are at B. At C, that is a quarter a cycle. At B, it is going to be half a cycle. So this is a quarter a cycle when we come back. So you have moved like this. Then we have come back half a cycle. Then when we reach A, of course, by reaching A, I think that would be 3/4. So this is 0, a quarter, half, 3/4. And when we come back to B, it is going to be a full cycle. So I think that one is obvious. 3/4 at A, and at B, it is going to be a full cycle, which is going to be period. Then for displacement at B, it is 0. If we say at C, it is x naught, that is maximum displacement. Coming back to B, it is 0. Going to A, it is going to be negative x naught because it is on the other side. If to the right is positive, then to the left it is negative. Okay, so let's predict the velocity at B. Of course, at B, the body is moving with the maximum speed because B is equilibrium. So we expect B, the velocity, to be maximum V naught. Then at C, because C is the maximum displacement, at maximum displacement, velocity goes to 0. Then at B again, we are coming back to equilibrium. But remember, we say to the right it is positive, to the left is negative. So this is going to be negative V naught, maximum velocity, but in the opposite direction. Then at A, velocity again goes to 0 because it is at maximum displacement. Then coming back to B, we are now moving to the right. So I think this is going to be positive V naught. So we start with a positive V naught if we are moving to the right, then 0, negative V naught, 0, positive V naught, 0, negative V naught, and so on and so forth. So the process continues like that. Then the acceleration, we have already seen that acceleration equals to negative omega squared x naught. So, omega squared x. And when the displacement is x, when the displacement is 0, the acceleration is 0. So at B, we expect the acceleration to be 0. At B, the acceleration is going to be 0. At B, the acceleration is going to be 0. Whenever the acceleration is 0, the displacement is, whenever the displacement is 0, the acceleration is expected to be 0. Then whenever the displacement is maximum, like at C and A, the acceleration is going to be maximum. However, when the displacement is positive, the acceleration is negative. When the displacement is negative, the acceleration is positive because they are always in opposite directions. So here the displacement is positive. We expect the acceleration to be negative. So this would be negative A naught. When the displacement is negative, we expect the acceleration to be positive. So this is going to be positive A naught because maximum acceleration is equal to omega squared times x naught. So when displacement is maximum, the acceleration is maximum. Then kinetic energy at B, remember whenever we are passing equilibrium, the speed is maximum. So kinetic energy at B is maximum. So this is going to be E K maximum. Whenever the displacement is 0, it is going to be maximum, EK0 maximum, EK0 maximum. And then whenever the displacement is maximum, the kinetic energy goes to 0. So this is going to be 0. This is going to be 0 whenever the displacement is maximum. Then for potential energy, we note that potential energy is whenever we are passing equilibrium, the vertical height was 0, so potential energy is going to be 0 whenever we are passing equilibrium. So this is 0, 0, this is going to be 0 because the displacement is 0. But whenever displacement was maximum, potential energy was maximum, so this is E potential maximum. This is going to be E potential maximum. The subscript O there is referring to maximum. So I think that is the summary of all these variations as we have discussed them. Okay, so I think that is the table which summarizes all these quantities that I've been discussing all along, right from lesson 2 up to this point. So that is the summary of all the quantities that we need under simple harmonic motion. Then I can also give another summary for all the graphs that we may need to know for simple harmonic motion. So this summarizes all the graphs for simple harmonic motion. Remember, the velocity and the displacement are always if the displacement is to one side, the displacement becomes maximum, the velocity becomes 0. And if the displacement becomes 0, the velocity becomes maximum. A graph of displacement against time, that one we already know from AS. A graph of velocity against displacement is an oval shape. And of course, a graph of velocity against time is a cosine curve. Then a graph of acceleration against displacement was a straight line through the origin. And you should be able to sketch a graph of acceleration against time. This is just for one complete cycle. You should be able to sketch a graph of energy against displacement for potential and for kinetic, and even for one complete cycle as demonstrated down here. So that is the summary of all the graphs we need to know for energy against time, energy against displacement, acceleration against displacement, acceleration against time, velocity against time, and displacement against time. Like I said, you cannot cram all these graphs, but you can use first principles to arrive at those graphs by simple calculations, as we have seen previously. Okay, I think we now qualify to do a few examples and we close this chapter. A pendulum. A pendulum bob of mass 120 grams, so this is M, oscillates in a simple harmonic motion with angular frequency of 12.6 radians per second and amplitude 30 millimeters. Calculate the total energy. Total energy. So of course I said for total energy you can get kinetic plus potential and you arrive at total energy. But from experience and good practice, total energy is E naught is a constant which is a half m omega squared times x naught squared. Everything here is a constant, that is total energy. So we have the mass, we have the frequency, we have the angular frequency which is omega, and we have the amplitude. So I will just substitute from here. So this will be a half times 120 times 10 to the power of minus 3 times omega is 12.6, but this should be squared times x naught squared, which is the amplitude, that is 30 times 10 to the power of minus 2. I mean minus 3, but this should also be squared. So I'll press my calculator here. So from my calculator, I'm getting this as being equal to 8.6 times 10 to the power of minus 3 joules, or 8.6 millijoules. Then the kinetic energy and the potential energy is at half amplitude, So let's check for kinetic energy. Remember, kinetic energy is given by a half m omega squared into x naught squared minus x squared. And when we substitute, we have a half times the mass is 120 grams, which is 0.12 times times omega, which is 12.6, but it is squared, into the amplitude is 30, I think 30 is 0.03 squared minus half amplitude is 15 millimeters, which is going to be 0.015 squared. So I'll press my calculator. Okay, so from my calculator, this is 6.4 times 10 to the power of minus 3 joules. Then the potential energy at half amplitude, potential energy is a half m omega squared x squared. Now students normally confuse potential energy and total energy. Instead of x squared for potential, they use x naught. They end up getting the same as total energy. So this is going to be a half times 0.12 times 12.6 squared times the x here is a half amplitude, which is 0.015 squared. So I'll press my calculator. So from my calculator, this is giving me 2.1 times 10 to the power of minus 3 joules. I have to check the previous one again because the sum are must be the same. Okay, let me write this to more significant figures then. The first one was 8.57, and this is supposed to be to more significant figures 6.43, and this is supposed to be 2.14. Okay, so we shall notice that if we were to add kinetic energy plus potential energy, we will get 6.43 plus 2.14 times 10 to the power of minus 3 joules. And this is the same as 8.5, I think, 7 times 10 to the power of minus 3 joules. So it's like the sum of potential and kinetic is always going to be equal to the total energy. Okay, example number 2. A particle of mass 0.4 kilograms oscillates in simple harmonic motion with frequency 5 Hz and amplitude 12 centimeters. Calculate for the particle at displacement 10 centimeters, kinetic energy, potential energy, and total energy. Okay, so for kinetic energy, we know that kinetic energy is equal to a half m omega squared into x naught squared minus x squared. So I'm substituting to becomes a half times the mass, which is 0.4 times omega. They've given us the frequency, so it means omega is equal to 2 pi times f. So omega is going to be 2 pi times 5, which is going to be 10 pi radians per second. So I'll just simply say times 10 pi, but this is squared, into x naught is going to be 0.12 squared minus at a displacement of 10 centimeters, so that is 0.1 squared. So I have to check my calculator. So this is giving me kinetic energy as 0.87 joules. Then potential energy, so you have that potential energy is equal to a half m omega squared x squared, which is going to be equal to a half times 0.4 times 10 to the 10 of pi, 10 pi squared, then times x, which is 10 centimeters, that is 0.1 squared. So this is giving me 1.97 joules as the potential energy. So I can predict that total energy, or I can write E total like that, is going to be the sum of kinetic plus the sum of potential, which will be 0.87 plus 1.97, which is going to be equal to 2.84 joules. Alternatively, I could use total energy as being equal to a half m omega squared times x naught squared, and I substitute, this will be a half times 0.4 times 10 to the pi 10 pi squared times x naught squared, which is 0.12 squared. And I guess the answer is the same, times 0.4 times 0.12 squared. 0.12 squared, 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 0.12 squa then times 10 pi squared. So the answer is essentially the same, 2.84 joules. So the answer is either the sum of the two or just using the constant potential energy. I think that is a good example for using that expression. A particle of mass 60 grams oscillates in simple harmonic motion with angular frequency of 6.3 radians. So this is going to be omega. And amplitude of 15 millimeters. So this is x naught. Calculate total energy. So we have just seen total energy is equal to a half m omega squared x naught squared. So this is a half times 60 times 10 to the power of minus 3 to change the mass to kilograms times 6.3, but this is squared, then times 15 times 10 to the power of minus 3, and this is also squared. So this should be able to give you a total energy 0.5 times 60 exponent minus 3, then times 6.3 squared, then times 15 exponent minus 3, but this is squared. So this is 2.7 times 10 to the power of minus 4 joules. The kinetic energy and potential energy at half amplitude, that is at the displacement which is a half. So of course I will find the kinetic energy as a half times the mass, which is 60 times 10 to the power of minus 3, then times omega, which is 6.3 squared, then into x naught, which is 15 times 10 to the power of minus 3, but this is squared, minus 7.5 times 10 to the power of minus 3, and this is also squared. So I'll just press my calculator. So 15 exponent minus 3 squared minus 7.5 exponent minus 3 squared, then times 6.3 squared times 60 exponent minus 3 divided by 2. So this is 2.0 times 10 to the power of minus 4 joules. So then for potential energy, it will be a half times 60 times 10 to the power of minus 3 times 6.3 squared, then times x squared. So this is going to be times x squared, which is 7.5 times 10 to the power of minus 3. And this is going to be squared. So 7.5 exponent minus 3 squared times 6.3 squared, then times 60 exponent minus 3, then divide by 2. So this is giving us 0.7 times 10 to the power of, let me see, 1, 2, 3, 4, 5. Okay, I want to write more significant figures, so I'll write more significant figures. So let me write 6.7 times 10 to the power of 1, 2, 3, 4, 5. That's power minus 5 joules. So if I had written more significant figures, of course, the sum would be the same. Sketch graphs to show how each of the following quantities change during the course of a single complete cycle of undamped pendulum: kinetic energy, potential energy, and total energy. So we have sketched this for a single cycle. We'll still sketch it for you here. For a single cycle, we have already sketched this. Remember, it is energy against time, so both of them are scalars. So energy against time. So I'm going to divide this into 4 parts: 0, a quarter of a cycle, half of a cycle, 3/4 of a cycle, and then 1 complete cycle. If we set t equals to 0 when x equals to 0, that is passing equilibrium, it means kinetic energy is going to be maximum and potential energy will be 0. So I'll start with the kinetic energy. At t equals to 0, x is 0, so kinetic energy will be maximum at t equals to 0. Then it goes to 0, it comes back to maximum, it goes to 0, back to maximum. So kinetic energy will be like this. Then, of course, when kinetic energy is 0, potential energy is when kinetic energy is maximum, potential energy is 0. So this is starting from here. When at a quarter cycle, displacement is maximum, so this goes to maximum, back to 0, maximum, back to 0. So this will be something like this. So this is going to be kinetic energy, and this is going to be potential energy. But then for total energy, it is a constant, so for total energy, it is going to be a horizontal line. Total energy, you just put the ruler and draw a straight horizontal line. That is for total energy. Because total energy is a constant, so it is a horizontal line. Okay. So something like that, you can sketch a better graph than mine. You could sketch a better one than mine. Okay. The figure below shows how the different forms of energy change with the displacement during simple harmonic motion. Copy the graph and show how the graph would differ if the oscillating mass were given only half the initial input. Only half of the initial input. Copy the graph and show how the graph would differ if the oscillating mass were given only half of the initial input energy. So the energy is simply half. The energy is simply going to be half. So I have to recopy this and resketch this. But instead of sketching a new graph, I'm just going to use a different color. I think I should. Anyway, let me sketch a new one. So it is energy against displacement. So I'll draw the axis for displacement between negative x naught and positive x naught. So this is going to be 0. Remember, total energy remains constant, but they said it is given only half of the initial input. So half of this should be somewhere here. So it means total energy is going to be half. So this horizontal line is representing energy, half of the total is representing total energy. So total energy is going to be half. Yeah, total energy is going to be half. But of course, the shapes are not going to change. So red was kinetic energy, so I'll sketch the new graph for kinetic energy. And they said copy the graph and show. So it means I can sketch on the same graph. So there is no need of drawing a new one. Okay, so total energy is going to be half of the initial total energy. So this horizontal line, let me use a green. So the new total energy is going to be this one here. So this is going to be E total. This is going to be total energy. Then kinetic energy, of course, the graph remains almost the same. So this is going to be the graph for kinetic energy, same shape. And the graph for potential energy is going to be same shape. Let me choose the color for potential. So this is going to be potential, and this is going to be kinetic energy. So that is if the total energy was half of, or was meant to be half of the initial energy. Okay, so I think that is fine. The figure shows how the velocity v of a 2.0 kilogram mass was found to vary with time t during an investigation of simple harmonic motion of a pendulum. Use the graph to estimate the following for the mass. The maximum velocity, that one you just look at the graph here. Maximum velocity, you just look at the graph. And I think that value is 0.35. So this is 0.35 meters per second. Maximum kinetic energy. Maximum kinetic energy. So if I have the maximum velocity, then maximum kinetic energy is the same as total energy. So it can be considered to be a half m omega squared. Since I have maximum velocity, I can even use the equation for kinetic energy. So this can be also equal to a half times mass times the maximum velocity v naught squared. So this would be a half times 2 times 0.35 squared. So 0.35 squared times 2 divide by 2. So this is 0.12 joules. Then maximum potential energy. This was maximum kinetic energy, maximum potential energy. Of course, for simple harmonic motion, the maximum potential energy is going to be the same as the maximum kinetic energy. So this is going to be 0.12 joules. Because when kinetic energy is maximum, potential is minimum, 0. So it means by the time potential energy becomes maximum, then kinetic energy must have gone to 0. So this is also going to be 0.12 joules. Its maximum acceleration. Remember, acceleration is maximum when the displacement is maximum. So maximum acceleration is given by omega squared x naught. And remember, maximum velocity is also given by omega times x naught. So it means we can now combine these two equations. And we say that maximum acceleration, so this means maximum acceleration can be equal to omega times v naught, which means we can just multiply omega with v naught. We have maximum velocity. Omega, I can use the graph to find omega. So omega is going to be equal to pi over t, where the period is equal to, what is the period here? Okay, I think the period is approximately It is hard for me to see the period here. Okay, 1.0. Each small box is 0.02. Okay, 1, 2, 3. So that is 0.26. I think that is 0.26. So this is 2 pi divided by 1.26. That is the period, I think. So this is going to be 2 pi divided by 1.26, then times V naught, which is 0.35. So this is going to be equal to 2 pi divided by 1.26, then times 0.35, which gives me 1.7 meters. Yes, 1.7. This is 1.7 meters per second. That is 1.7 meters per second. Then the maximum restoring force, of course, force is equal to mass times acceleration. So this is going to be maximum. It's going to be the mass times the maximum acceleration, which is 1.7, and this is going to give us 3.4 newtons. So I think these are going to be the answers to this question. And I think for now we can really stop there. So this is a summary of everything we have mentioned in simple harmonic motion. We mentioned, of course, we refer to the radians. We talked about these solutions. That should be part of you now. When we use cos and sine, we now know what amplitude is. We know the period. We now know when to use omega equals 2 pi over t or 2 pi over f. The concepts of angular frequency, sometimes angular velocity is going to be used in the place for angular frequency to mean the same thing. We now know maximum amplitude, frequency, and so on and so forth. So that is a summary of oscillations relating them to simple harmonic motion. And I think that should be the end of simple harmonic motion. Do not forget to go to the solved past paper questions if you want to gain more confidence. Until next time, bye bye.